A very warm welcome to IPS 128, Statistical Literacy Across Disciplines. The session aims to impart knowledge of statistical techniques of conducting experiments to gather data, to check authenticity and quality of data, to make possible inferences out of data and make appropriate daily life decisions based on the inferences. We have three invited speakers in the session, and Professor Olawale Au is chairing the session. Professor Olawale Au is an elected member of the prestigious ISI and an affiliate member of Asian Academy of Sciences. He is a professor and PhD advisor at Global Humanistic University, Curacao. He is presently the LISA 2020 Engagement Ambassador to Africa. I would now request Professor Olawale Au to introduce to the speakers and call them for their presentations. Over to you, Olawale Au.
Thank you very much, Richard. Want to welcome everyone to this session. Like Richard has said, this is IPS 128, Statistical Literacy Across Disciplines, being organized by Professor Richard Vassa. Today we have three distinguished speakers in this session. We are going to hear about some interesting topics. Today we want to begin with the first speaker. Introduce the three speakers briefly. I have with me here Professor of UFRN Natal in Brazil. Professor Carla Vivacqua is a full professor of statistics at the UFRN in Natal in Brazil. She's an expert in experimental design, and she has influenced so many students. She has attended so many conferences, and she has presented papers. She has a lot of publications to her credit, and she is also an elected member of the ISI. She's going to be talking to us today on the topic titled Key Concepts to Develop Statistical Literacy on Understanding Experiment. Key concepts to statistical literacy on understanding experiments. Another speaker we are going to listen to today is Professor Arun Sinha. Professor Statistics is a retired professor of statistics at and is an expert in quality control. He has supervised so many students. Is an elected member of the ISI, and is a really, it's really nice to have him here with us today. Professor Sinha will be talking to us about control charts and capability analysis for statistical process control. And lastly, we have the speaker, the organizer of the IPS 128 herself, Professor Richard Vassa. She is an assistant professor of statistics at the Central University of Southern Bahia in India. She has expertise in the area of Bayesian modeling and computational statistics. And she is a mentor to so many students. And today, in this IPS session, she's going to be talking to us on uncertainty evaluation with the concepts of Bayesian statistics. I want to welcome you again to this session. Without taking much time, we want to quickly move over to the first speaker in person of Professor Carla Vivakwa, who is talking to us on the title Key Concepts to Develop Statistical Literacy on Understanding Experiments. Over to you, Professor Carla Vivakwa.
Thank you very much for the invitation. It's a pleasure to be part of this session. Welcome to the IPS on statistical literacy and across disciplines. I'll be talking about key concepts to develop statistical literacy on specifically understanding experiments. As the outline of this presentation, I will briefly talk about statistical literacy and its relevance, and then focus on the main topic of this talk, that is understanding and interpreting experiments and its key concepts. Statistical literacy involves the ability to read and interpret data. With that, it enables us to use the statistics as evidence in discussions and arguments. It is essential to all citizens. It helps us to fully function in society. With a clear understanding of data and statistics, we can provide basis for our discussions. But to be able to do that effectively, we require critical thinking about statistics. It's a key point to be able to have statistical literacy. And I will be talking about some specific issues which motivated this talk. We are facing the COVID-19 pandemic. And during this part, we have been dealing with many issues regarding communication and misinformation. So statistics and data analysis and interpretation plays a key role in this whole situation. We need to change the way society interacts with data, statistics, and science. And statistical literacy is a key point to that. So all this pandemic is a warning to us scientists to make it the statistical language available to all the communities. I will try to address this issue specifically regarding experiments. I will briefly talk about how we can understand and get a basic understanding of the principles of experimentation, the key concepts. What are the components of an experiment, and which are the basic principles that we use when design and interpret experiments. We have one key point when you want to understand experiments. The first is to differentiate between observational and experimental studies. Observational studies, they are restricted to the observation of the variables of interest. There is no interference in the observed process. While in experimental study, there is an attempt to take control of the situation and have specific control how the observations are made. So this is key to experimental study. Let's see an example to make it clear. Observation study is passive. So data is collected and we have no interference. But in an experimental study, we have active actions. So data is collected based on carefully planned interference in the process. Let's suppose that you want to study the effect of the temperature in the task of assembling a car. So how would you do an observational study? As the name says, we just observe the environment. We will go to the factory in specific days and we will observe what's the temperature and how is the assembly going. How would it be an experimental study? We would have to take some control over the environment. We will need to control the temperature in the assembly line. So we'll be changing the temperature and evaluating the impact of this change on the production line. We'll make all these changes that will be planned. For example, if you want to study 18 degrees Celsius, 20 degrees Celsius, 25 degrees Celsius, we are going to increase the temperature and see what will happen with the production. In an observational study, we'll just take notes of the temperatures that are in that moment that we are going to observe. So we have some differences. When we are doing an experimental study, we have this control. We can choose the temperature that we want to test. But if we are in an observational study, we don't have this control. So we are subjected to the temperature that will be on the days that we are observing. So this is a basic difference between observational and an experimental study. Let's go a little more with some components of an experiment. The first step is if you identify if it's an observational or an experimental study. If you are in an experimental study, there are two basic components that are present in any experiment. The first one is the responsible variable. It's the main characteristic of interest, which will be measured during the study. In the example of the car, we can use the time to assemble the car as our main responsible variable. There are experiments which consider only one variable, but you can have several responsive variables. Another key component of an experiment is the factor. That is the main point. The factor is the one that we control. It's the variable that you are controlling. In this example, it's the temperature. So we can set the values of the temperature. So the values that the temperature will be assuming in the experiment are called levels. So to summarize, we have key points to understand an experiment. First, to identify if it's an observational study or if it's an experiment. And if it's an experiment, we'll identify its components. The basic components are the responsive variables and the factors. The factors will determine if it's an experiment. They are the variables that are being controlled in the experiment. To run a good experiment, we need to take care of other variables. We are interested, in this case, just the temperature and the time to perform the task. But if you analyze the time to assemble a car, there are several other variables that affect this variable. So we need to make them fixed. In an experiment, we have to vary just one element, that is the factors. We just change the factors. The other elements we keep constant. With that, we can establish cause and effect relationship. That's the main advantage of an experiment. It's the study that allows us to establish cause and effect relationships. In this example, if you can control all the other variables, like the team that are assembling the car, the materials, if all of them are fixed and we are only changing the temperature, if you observe a difference in the time to assemble the car, we can say that what the cause of that effect is the change in the temperature. But if we vary other variables at the same time, so we lose this characteristic. For example, if you change the temperature and also the team that is assembling the car. So if we observe a change in the production time, we cannot say if its cause is the change in the team, the change in the temperature, or both. So it's important to take control of other possible variables that can affect our response variable. To do that, to have a better understanding of the situation, we use basic principles. There are three basic principles in experimentation: blocking, randomization, and replication. These are strategies that a designer use to plan the experiment. Here, I wanted to show just a brief overview of the basic principles of experiment. So, I'd like to thank you for your time, and I'm giving you my contact information, so I'll be pleased to talk to you about more details about the experimentation. Thank you.
Thank you very much, Professor Kala, for this great talk. We really enjoyed that talk. I'm sure there will be comments soon. Now, I want to quickly move on to the next speaker, Professor Arun Sinha, who is going to be talking to us about control charts and capability analysis for statistical process controls. Professor Sinha, over to you now.
Yes, I have already recorded my presentations. I just played it. Risha, please play this.
Okay, trying again.
Control, this is title of the topic is control charts and capability analysis for a statistical process control. Now, background, we know that variation is inherent in nature, but we wish to produce items of uniform quality because we cannot produce identical items. It is interesting to note that even our signatures and handwritings are not identical. It has been observed that in general, good quality items or products become cheaper in the long run because of the reduction in the wastage and the presence of a quality control unit in any organization. This could be achieved more systematically by using a statistical quality control techniques. This technique was initially proposed and developed by Shewhart in 1924. Now, a phenomenon is said to be controlled when through the use of past experience, we can predict at least within limits how the phenomenon may be expected to vary in the future. It is understood that for prediction within limits means that we can state at least approximately the probability that the observed phenomenon will fall within the given limits. Now, basic of control charts, if T denotes the statistic of a characteristic of interest, then we have upper control limit UCL equal to expected value of T plus 3 times standard error of T. CL equal to expected T, and LCL, lower control limit, is equal to expected T minus 3 times the standard of T, where expected T denotes the expected value of T, while ACE stands for standard error of T. This is referred to as the control charts based on 3 sigma limits. The concept of 3 sigma limits has been observed reasonably well for all practical situations. It is a compromise between 2 and 3 sigma limits. Even in non-normal situations, this works well because of St. Limit theorem and Savage inequality. A control chart is a graphical statistical technique to examine whether a process is under a statistical control. If a point exceeds the upper control limit or falls below the lower control limit, this suggests that the process is out of a statistical control. These scenarios in turn indicate the presence of one or more special or assignable causes of variation which have led the process out of a statistical control. Though the statistical control was initially developed to check the current status of the process or manufacturing process by Shewhart in 1924, but with the passage of time, this technique has become very popular for examining the process of services sectors too. A process to be under statistical control if all points lie within the upper and control limits, but if a point exceeds UCL or falls below LCL, the process is said to be out of statistical control. In these situations, all points that go outside the control limits are removed from the given data set and fresh control limits with the remaining observations are computed. Again, the remaining points are plotted with the new control limits. The process is continued until all points lie within the control limits. This is referred to as the final control chart, while the first control chart is known as the trial control chart. Now, we usually come across the following two types of data in both manufacturing and service sectors. Data for variable control charts include X bar, R, sigma chart. Data now next for attribute control charts. The control chart for fraction defective or fraction non-conforming is called P chart. The control chart for non-conformity, is also called defects, is C and U chart. Now we discuss variable control charts. In general, we first examine whether a process is under control with respect to process variability, and once the process is controlled, found under statistical control, then the status of process average is examined. The process average, we have two types of X-bar chart that is based on involving range and involving standard deviation. For process variability, we have two charts which include R chart and sigma chart. To study the aspect of service quality that reflect to the amount of time it takes to deliver luggage as measured from the time the guest completes check-in, proceeds to time the luggage arrives in the guest room. Data were recorded over a 4-week period. Subgroups of 5 deliveries were selected from the evening shift each day for analysis. The data are given below. Next page on summarizes the results for all 28 days. The hotel management has issued a policy that 99% of all luggage deliveries must be completed in 14 minutes or less. Now this is data set is given for 28 days and each day we have 5 observations. We need to draw control charts to examine the current status of the hotel service quality, to examine whether the process is capable of meeting the 99% goal set forth by the hotel management. Third is to calculate the CPU for measuring the process performance. Now solution of one. Table A1 is gives mean and range of delivery of luggage times for all 28 days. This is given. Now the control charts for R charts are obtained. UCL is equal to 7.361, central line CL is 3.482 and LCL lower limit is 0. R chart for luggage deliveries times is depicted using minute of 19 in figure 1. It does not indicate any range value outside the control limits or any clear pattern. This means that the process is in a statistical control, free from a special causes of variation. This chart is given. We find that all points lie between UCL and LCL. Now, the R chart shows that the process is in control with respect to the process variability. We next plot the X bar chart to examine the current status of the process with respect to the process average. Now for control limits for X bar chart, we have obtained UCL, central line, and LCL. Now figure 2 displays the X bar chart for luggage delivery times, which does not disclose any average value of the luggage delivery time outside the control limits. This in turn helps conclude that the process is in statistical control with respect to the process average. As both R chart and X bar chart are in control, we conclude that the luggage delivery process is in a state of statistical control. This is the graph for X bar chart. We find that all no value exceeds UCL or falls below LCL, the process is under control. Now attributes control charts. P chart or control chart for fraction, defective, or proportion non-conforming is used. For P chart, characteristics are observed by classifying the items into 2 classes or groups, usually defective or non-defective with binomial distribution to obtain mean and standard deviation of the proportion of defectives. Now we have given one illustration for 12 days, and we have taken from Levin and their SSI into 2016. We are given for 32 days, and the proportion of defectives are given for all this. Next. Now we have got n is equal to 5, p bar is nothing but total number of non-conforming items, total items inspected. So we have got UCL, LCL, and LCL, and figure 3 gives the graph. Now this is the graph for P charts, and again we find that no date this proportion exceeds UCL or fall below LCL. Of course, in case of below LCL, we say it is okay. Next. Now control charts for non-conformity defects. Failure to meet a specification is a point results in a defect or non-conformity, and C chart is plotted for defects or non-conformities per unit. Now the unit is considered maybe a single unit or a group of items, part of an etc. There are numerous opportunities for defects to occur on an given item. So, but the probability of occurrence of a defect is very small. Due to these reasons, the statistical theory for C chart is based on the Poisson distribution. Now we have given an illustration that was given by Levin and others in 2016. The following data were collected on the number of non-conformities per unit for 10 time periods. So we are given time for 10 days, and non-conformity defects per unit are observed. Now we need to construct a control charts for this chart, C chart. Now solution, we get that C bar, average defects 11.5, we have got UCL and central line, LCL. The control chart is shown in figure 4. S time 1 observation is above UCL, that reveals that the process is not in a statistical control because of the presence of some special causes of variation. The chart is given, is find that on day 1, it takes defects exceed upper control limit. Now we discuss capability analysis. For analyzing the capability process, we estimate the percentage of products or services that are within the specifications. Assuming that the process is in control X is approximately normal, we can estimate the probability of a process outcome being within the specifications. Now, if the lower specific limit and upper limit is able to be represented by LCL and LSL and USL respectively, then quality of outcome within the specifications, the line between LCL and UCL is given, and we calculate that Z is equal to LSL minus X bar divided by R bar by D2. Similarly, Z should be less than USL minus X bar divided by R bar by D2. Next. Now, see this for second and third part of illustration of X1 and R chart. It is further mentioned that the hotel management has instituted a policy that 99% of the luggage delivery must be completed in 14 minutes or less. Here USL is 14, N is 5X, double bar is 9.478, and R bar is given 3.482, and D2 is a constant that is equal to 2.326. Now, probability of outcome within upper control limits is given Z less than USL and minus X bar divided by R bar by D2, and this probability comes as 0.99874, assuming that it's a normal distribution. Now, this suggests that 99.874 of the luggage deliveries will be made within the specified time. We therefore conclude that the process is capable of meeting the goal of 99% set forth by the hotel management. As CPU is equal to, we get 1.01. This indicates that USL is slightly more than 3 standard deviation above the mean. Now, scenarios in developing countries, statistical process control (SPC) techniques played a very important role to help rebuild the economic conditions of Japan after the Second World War under the supervision of W.E. Deming, a US expert of statistical quality control and improvement. In developing countries, SPC techniques can help improve their economic conditions tremendously if employed properly because of their cheap labor and abundance of natural resources. Now, Badnar and Mahoba in 2016 described the applications of SPC in Zimbabwean manufacturing industry. Of course, they have not mentioned the data set. They also discussed the existing associated problems with the manufacturing industry there, which could be minimized. Again, APU and others in 2018 used the data set of garments producing companies known as Silver Spark Apparel Limited, a Raymond Group company, India, for an illustration. There are good garment companies in Ethiopia, China, India, etc., and other countries, in other industries in developing countries, which could contribute to the incomes of their countries considerably using the SPC techniques. Those countries could enhance their economies using statistical quality control techniques in a shorter time frame. Now we are given the references, Abtive, Pro P, and PU in 2018. Again, they have given Levin and Stephen and Silva book. Next, Madeleine and Mohobi, 2016. And Montgomery book published in 2009 edition, it is 6th edition. And the Sheward paper that appeared in 1924. Thank you very much for your patience and interest.
Thank you very much, Professor Sinha, for that interesting and incisive, educative talk. Thank you. Lastly, today, we want to listen to Professor Vatsa. She is the organizer of this IPS, and she's going to be talking about an important topic. Our talk will be on uncertainty evaluation with the concept of Bayesian statistics. Over to you, Richard.
Thank you so much, Professor Olawale. I'm sharing my screen for the presentation. Okay, so the title of my talk is Uncertainty Evaluation with the Concepts of Bayesian Statistics. In this talk, you will see what is uncertainty in real life and how we quantify it using the Bayesian concepts. Our daily life is managed by two types of events, deterministic and uncertain. Deterministic events are fixed, they're bound to happen, and we cannot avoid them. And uncertain situations are random in nature, and they may result in different possible consequences when replicated. For example, weather condition, election results, occurrence of disease, stock market prices, these are all random in nature. Thus, an uncertain scenario leaves us with different alternatives to choose from. It requires proper planning and decision making to choose the best alternative in order to live life securely and comfortably. If we knew a consequence of an uncertain scenario, it would have been very possible and good for decision making, but it may not be actually possible in reality. So we go for the quantification of uncertainty. It shall make it easier to determine the optimum decision of life. In his book, Professor C.R. Rao, his book title is Statistics and Truth, Putting Chance to Work. He says that uncertain knowledge plus knowledge of amount of uncertainty in it, that is equal to usable knowledge. So we quantify uncertainty. Probability theory has been the oldest concept for it. There are two approaches to it, the frequentist and the Bayesian. The frequentist approach is based on repeating a phenomena in long run and counting down the number of its consequences. Whereas Bayesian is based on looking for prior knowledge or judgment around an uncertainty of a phenomena and quantify the probability. The Bayesian approach is more suitable for real-life scenarios, which may not be replicated in long run and in under similar conditions. For example, eruption of volcano, rain tomorrow. In frequentist approach, measuring uncertainty of a phenomena begin with estimating the generating process. So what do we mean by that? Is suppose a phenomena results in infinite number of consequences. So it will be very difficult to count down the number of happening of the consequences and presenting the probability for them. So it rather better for a general purpose that we model the uncertainty around the phenomena using a probability model about some characteristic of the phenomena known as the model parameters. In Bayesian statistics, the data, the observed facts around the uncertainty of the phenomena, they are fixed. The uncertainty lies around the true value of the unknown parameters. They are quantified, the uncertainty is quantified and presented with probabilistic statements conditioned on the available facts. There are two types of uncertainty quantification in Bayesian statistics: prior density and posterior density. The prior density is the quantification of prior knowledge or judgment around the uncertainty of the parameter, whereas the posterior density is combination of prior and present knowledge formulation of a parameter. The posterior density leads to further summarized uncertainty measurements in parameters assessed by Bayesian point estimates and credible or highest posterior density regions or intervals. We may also be interested in predicting future events. So the uncertainty in a future event in Bayesian statistic is predicted through posterior predictive densities given current observations and summing over the posterior uncertainty in parameters. There's a very important concept in Bayesian and key concept that the parameters are considered random, unlike in the frequentist approach. Why is that so? Because the Bayesian paradigm is based on the subjective notion of probability. There may be different values of an unknown parameter under different hypotheses, thus accounting for its uncertainty. So the randomness in a parameter is not because of the variability in its values, like we consider randomness in data. Rather, the randomness in a parameter is because its true value is unknown and there is uncertainty about it. Let us understand Bayesian concepts. and it's evaluation of uncertainty with a simple example of electoral polls. Candidate has got 54 votes and B received 46 votes in a 100 people poll. So the question is, what are the chances of A winning the election? Further, what is the probability that any voter enrolled shall vote for B? The first question is about calculating the posterior distribution of A winning the election, and second is the posterior predictive probability that A voter shall vote for the candidate B. So we proceed finding out the posterior probabilities by setting up first, setting up a prior density, define likelihood, and compute the posterior density lastly. So depending on the prior information, we can set up the prior density differently. So for the first case, let's suppose we have no prior knowledge. So we can assign equal weightage to each value of the parameter is range. So we can consider uniform prior for that. And let's suppose here theta be that a voter chooses candidate A, right? The chances of choosing candidate A, that is theta. For no prior information, uniform density is assigned as the prior density. Further, suppose another piece of information comes in that candidate A is, chances of winning. So this means that theta must be greater than 0.5. Then only the candidate A can win. So to account for this information, theta greater than 0.5, consider the beta PDF as the prior distribution with the parameters or the hyperparameters A is equal to 4 and B is equal to 2.5. Further, let's suppose another piece of information we got as B, candidate B is more preferential candidate. And this can happen only if theta is less than 0.5. This means that the winning chances of candidate A is less, so that the winning chances of candidate B is more. So to account for this information, we can use again beta density as a prior distribution with hyperparameters as A is equal to 2.5 and B is equal to 4. The beta density here is used as the prior density because it matches the properties of theta lying between 0 and 1. And the beta density is also conjugate prior, and there are some classification of prior density that is fulfilled with this beta density here. Now we go for the computation of likelihood. Let's suppose X denote number of votes to candidate A. So the likelihood of theta given X is equal to 54 votes to candidate A, that is equal to binomial probability of X is equal to 54 given 100 number of the number of trials as 100 and probability of success as theta. Now we can compute the posterior density. By Bayes' law, the posterior density is proportional to likelihood into prior. So under different prior assumptions, we've got different posterior densities given over here. Now we can see the comparison between these posterior densities using a graph. So I'm showing you that in the next slide. So the left-hand side of the figure, it shows our result for the 100 people poll data. Now we can see that the curves, these show the posterior distribution, different posterior distribution and with the assumption of different prior densities. We can see that the posterior densities are almost overlapped with each other. So this means that what prior they have chosen has no significant effect, because the data that we used, that was very strong. It was 100 sample size, with 100 sample size. So we've got the posterior distribution almost similar or overlapped. But here on the right hand side, I have result with 10 people poll. So now here we can see that the posterior densities for different prior choices are different. Actually, we can see them separately and they are not overlap. So this means that the prior choice is significant over here. So what we can conclude here that with weak data, the prior choices have significant effect, but rather with strong data, there is no significant effect of prior choice. So it is advisable, if we have not strong data with us, choose our prior wisely, because that will be reflected into the posterior density and our posterior inferences. We have got further estimation in form of posterior mode, and that was found 0.53. We have also got 95% HPD highest posterior density interval, and as the question said, to find out the winning chances of candidate A, we've got posterior probability of theta being greater than 0.5, and we got the answer as equal to 0.73. Further, the posterior predictive probabilities of a voter choosing for candidate A and B are 0.53 and 0.47 respectively. How did I get these results? I actually wrote my R codes. Because this question was lower dimensional, rather unidimensional case, we had only one theta to estimate or to find out the posterior distribution. I used in numerical integration, and by discretizing the space of theta over here, I could discretize. I could actually convert the integration into the summation using the numerical integration technique. I further wrote this piece of R code to find out the mode here. Further, this piece of code for the 95% HPD interval. We could also find out equal date 95% credible intervals as well. And here the codes for posterior predictive densities actually. I wrote my own codes, but there are packages available on our project, and we will see those in the references section. So we have reached to the conclusion that uncertainty is inherent in nature and cannot be avoided. However, it can be measured for making optimum decisions. Bayesian statistics based on the Bayes theorem combines prior knowledge about an uncertain event and facts around it and presents the posterior quantification of uncertainty. Bayesian statistic is straightforward to apply, and it follows a set rule to present the inferences. The prior choice is an important step in Bayesian inference. If data is strong, effect of different prior choice is negligible. I have my references over here. This is the package, R package learn base, and this provides the computation of the posterior and other posterior density and other posterior estimates, including the posterior predictive inferences for the simple examples. For complex models or examples, we can use other packages. There are a list of packages on this website and our project. So you can look for that. And I have some other important references for the Bayesian concepts. These are the important ones. I was lastly say that thank you very much for your patience and interest in my talk. Thank you so much. Thank you, Chair.
Thank you very much. Thank you very much, Richa, for that interesting talk. It's quite interesting. We have listened to interesting educative talks today. I want to say a very huge thank you to all the speakers. And we hope that there will be comments. You can reach out to the speakers directly or to me, the chair, or directly to the organizer, Professor Richa Vasta, through our email address. Richa, can you scroll to your, can you share your screen again and scroll to your email so that they can see before we wrap up this session?
Shall I just share, my email on just the whiteboard over here?
First page.
Yes,
is
sure,
here.
sure. Yeah. Or probably you can copy the email of the other two speakers.
All right.
Yes.
Given on the first page, there is no problem.
Okay.
Yeah.
I'm
And
just
we
So
must thank our chairman also on behalf, because he took so much time and he arranged everything for us.
Thank you, Prof. Yeah.
actually, the email addresses are provided in the talks, so audiences can, directly contact the speakers.
Great. Yeah, sure.
Yes. So I think.
Sure. Good. No problem. Yeah, that's it. Okay. Thank you so much.
Thank
At
you
this
so
point,
much
want to wrap up.
And conducting this
Yeah.
session so nicely, so positively.
Thank
Thank you so much. Thank you so much, all the speakers. You have, presented your talk so effortlessly and so full of information. Thank you, everyone. Thank you so much. And
Thank you.
thank you.
Thank you.
You all.
Thank you. Bye, everyone.